We've added an SD card interface to the RISC R32V2020 CPU design based on some modifications to Grant Searle's SD card design. We're using the A-ESTF V2 card, which we got on AliExpress for around $65. It uses an Altera EP4 with the 22 version, which is a lot of macro cells in memory. In the upper section up there, there's a spot marked mini SD card next to the buzzer and the VGA connector, and that's where the SD card gets plugged into. It uses the micro SD card. The VHDL code is based on Grant Searle's Multicomp project, and it was adapted by Neal Crook, and he has a page up on GitHub which describes what he did, but he extended it so it doesn't just work with SDXC cards, the smaller cards, which I think are up to 2 gigs, but it works with SDHC cards. We ended up buying an SDXC card, and that had some complications. Maybe we'll describe that in the video here. But basically it provides 5 addresses that you read or write to. Most of them are write. The only read one actually is the data and the status ones. But you write to the control address, the base address sections 0, 1, and 2, and he describes the definition of what goes into that. Most of BA0 would get padded inside of the controller to be zeros for 512 block sizes. That's what we set the controller to when we formatted it. SDXC cards typically want to use different file system. That just slipped my mind, but they use a different card system, file system than the HD cards use. So we ended up reformatting the card using a different utility to make it SDHC FAT32 file system compatible. Now there's no file system provided in this FPGA controller. It's just the control of the SPI lines that go out to the chip itself or to the TF or SDHC card. So that would all be done by higher level software. But we got the card basically working, reading and writing blocks, and we'll take a look at that here in this video. So this is the code that we wrote in R32V2020 assembly, and we've included all of the comments that were relevant from the VHDL file itself and the addresses that get written to. So basically, if you want to read a 32-byte block, then you wait for status to be 80, you write to the 3 addresses, and then you write 0 to the control to issue the read command. Then for the 512 bytes you want to write, you wait for SD status to be 0, and then you write the data out. And when you're done, it writes 512-byte block, and that is working. Writing is very similar, except in that case you write a 1 to the control, and instead of reading the byte, you write the byte to the SD data, and the status word you're looking for is A0, which indicates that it's ready to take a write block. So our exercising code is pretty similar. It basically, in this case, will set it to the second block, and then it'll do a write block to the card, and then we have code here that'll loop on reading all the blocks one at a time with hitting a character on the PS2 keyboard between. The read block code reads and dumps out a block of the 512 bytes, pushes everything it needs to push on the stack for all the registers it's going to use. Of course, at the end, it'll pull them back out again. But it sits and waits for that 80 value on the SD status ready for reads, and then it loads the what was passed in R8. You pass the block number to it, writes the LBA 0, 1, and 2, and then it writes 0 to that control register, sets up a count for a loop of 24, and it'll want to print a carriage return every 20 or 512, and every 24 it'll write a new line out to it. Then it sits and polls the status in a tight loop here looking for E0, and then writes out the actual character that was, or reads the character that was read from the SD card. So load peripheral byte, load a byte from the peripheral, and then it prints that to the screen with a space between them. So it turns that 8-bit binary into 2 ASCII digits, 0 through F, and then it goes through, subtracts 1 from the counter and reads the next byte, If it reaches an increment of 24, then it will go ahead and do a carriage return line feed and then reset that counter back to 24 again, and goes through all 512 in this whole loop here. And that's pretty much it. The loop here is the outer loop of reading the next block. Here's what the program looks like when it runs. At the top it prints the SDXC dump utility version 001 and prints the block address, which is all zeros in this case, and we fill the first two 512 byte blocks with AA, so that's what you see on the screen here, and then at the bottom it asks you to hit a key to continue. So let's step through the blocks and see what they look like. Again, the first block is all A's. Then we hit a key and the next block 200 or 512 is all A's, and then zeros after that, just showing that the card is still initialized. We formatted the card earlier and overwrote the boot block so it doesn't have the boot record stuff in for exFAT. Using a 64 gig card, which Windows doesn't let you format in any format other than the exFAT, and we wanted it to be in FAT32 so it would be compatible with other file systems, and there's really couldn't find a way to do it in Windows. Followed the procedure here on the AOMEI Partition Assistant page, and they say that if the card is over 32 gig you will not be able to format it by the traditional ways listed above. So we went through all that and proved they were right, even using disk partition, and ended up using it, their tool, the AOMEI Partition Assistant, to format it for FAT32, and that worked fine, although I don't know that we necessarily would have had to do that. Here's what the card showed up as in disk management under Windows 10. It shows up as an exFAT card, not a FAT32. It also has the first 16 megabytes as unallocated, and there probably is a way to shrink the partition here, but I think they're leaving that for boot records and things of that sort, which we don't really need, and I know we're overwriting that when we write to the first block on the card. But thought we'd just give it a go and try it, and it didn't work. To prove that, the only two options you get when you try to format it are exFAT and NTFS. Unfortunately, probably should have tried to find a smaller card, but they're getting harder to find. We were able to use the AOMEI to reformat it as FAT32, and that did work following the procedure on their page. So it not sponsored by them in any way, don't get any compensation from them, but they do seem to have something that works, and it is free, so seems like it's a good choice to do that. I don't know if there's any sneakware that gets in here anywhere. My computer didn't complain about it or pop up any malware or virus, but use your own caution, of course, downloading anything from the internet. So in the end, we have a pretty good set of utilities to work with the card, the SD card, that can read and write 512 byte blocks. I haven't done anything more with that other than test to see that it works. I powered the card off and on, and the memory was still there in the SD card, so it wasn't like we're magically inventing it or anything like that. Seemed to be a good solution, and the features that added, the SDHC capacity that was added by Neal Crook, is a very nice addition. I'll try to remember to put a link down in the show notes here that describe where to find that, but it's also on our GitHub. We've replicated up there. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindie where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.